Alright, silly people, here's the situation. You have two bodies, each with an independent heat capacity, heat transfer, and final temperature. Um, so you have a C1, a Q1, and a T1, a C2, a Q2, and a T2. And you're meant to prove that the final temperature of both of the objects together, they're placed in thermal contact, is given by C1 T1 plus C2 T2. I don't know why I put those parentheses. Um, Divided by C1 plus C2. Um, Using the definition of the heat capacities. Um, so to do that, um, the physics of the problem that you have to notice is that the sum of the heat capacities will be equal to the total heat transfer of the problem, which I'm going to call QF, uh, the derivative of that with respect to the final temperature. Um, it's just a superposition of the two different heat capacities. So we're going to solve these three differential equations individually and then combine them at the end to get that form of the final temperature. So um, you're going to look at the integral of C1 dt1, which will be equal to the integral of dq1. When you do that integral, you're just going to get C1 T1 is equal to Q1. You're also looking at C2 dt2 is equal to dq2. By the way, we're assuming that like the initial heat is 0. That way you don't have an integration constant. So C2 dt2 is equal to dq2. So C2 T2 is equal to Q2. And then the last differential equation is going to read the integral of C1 plus C2 dTF is equal to the integral of dQF, which when you integrate gives you TF times C1 plus C2 is equal to QF. Okay. Now, the total heat transfer for the problem is also just equal to the sum of the individual heat transfers, which we have forms for those already from the other two differential equations. So it's C1T1 plus C2T2 over here. And then to get the final form, you just divide both sides by C1 plus C2. Cool. If you really want to get into it, you can then be like, okay, what if C1 is much larger than C2? And then Blundell asks for a form of an approximation for the final temperature given by T1 plus C2 over C1 times T2 minus T1. To do that, we have to go back a step in algebra. So we're looking at this equation, TF times C1 plus C2 is equal to C1 T1 plus C2 T2. And we're going to subtract both sides by some physical quantity of the form C2 T1, right? And then, so this side is T2 minus T1. Cool. On the left-hand side, we can factor out a factor of C2, or actually just combine like terms. So you have TF um, times C1 minus or plus C2 TF minus C2 T1 is that stuff over there. Ugh. T2 minus T1. Well, TF minus T1 is really just approximately TF, because C1 has such a high heat capacity as compared to T2. Pretty much all of the change in temperature is going to be in the second object. The left-hand side will turn into TF C1 minus C2 no, plus C2. Yeah. And then on the right-hand side, still C1 T1 plus C2 T2 minus T1. Now we can be like, okay, C1 plus C2 is just approximately C1, because again, C1 is much larger than C2. And then say, so it's TF is equal to, or we'll just say TF C1 is equal to C1 T1 plus C2 T2 minus T1, and then divide both sides by C1. So you have T1 plus C2 over C1 times T1 minus T2 minus T1. I don't know why that approximation is useful. Maybe it has to do with the fact that C2 over C1 is going to be, by definition, a really small number, but T2 minus T1 is going to be a larger number for this to work. And so this term has an analytical ambiguity to it, which is useful to look at, I guess.